Welcome back, everyone. In this video, we're going to cover the hardware needed to build a Meshtactic repeater, go through some of the software setup, and finally do some range testing with our other nodes. So we'll compare the point-to-point distance between two nodes, and then the distance that we can reach with a repeater in the middle. We're going to use the built-in range test from Meshtactic, but also highlight some of its shortcomings and make some custom modifications to make this really robust and accurate. Let's quickly go over the hardware we need to build our self-sufficient solar-powered Meshtactic repeater. So first and foremost, we need our Meshtactic device, and any platform with the Nordic microcontroller is going to work well here. These are the most power efficient devices, and I suggest getting one without any GPS or screen installed. So the rack WizBlock Meshtactic starter kit is what we're using, and it's a really good option for this application. You don't want to use Meshtactic devices based off the ESP microcontroller, like the Heltec V3 here, because they're just less efficient and won't last as long with the same amount of solar light. So next we'll need our solar panel, and we're going to harvest ours from this garden light from Lowe's. The important thing to have is one with an integrated 18650 battery. That brings us to our upgraded battery, which we're going to replace in here. So this not only has a bit more capacity than the battery that comes with the garden light, but it's also got a protection circuit built in. So what this protection circuit will do is allow our device to reset if we're in the condition that the battery fully discharged because there was no sunlight for over a week. And when that sunlight comes back, this will allow the device to reset and power back on. Without that kind of circuit, like if we just use the unprotected cell that's in this garden light, these devices, the Nordic microcontroller specifically, they brown out and they don't come back alive unless you do a manual sort of reset. So we definitely don't want that. Now, there's a couple other ways to implement the protection circuit. You can actually convert the unprotected battery into a protected one with an external circuit. They sell these on Amazon, and I'll put that link in the description below. We'll need some double-sided tape to just affix our board inside the solar panel's housing, and we'll need a battery connector. This one I've found has the colors inverted, so just be careful if you get the same one. Ideally, you want one where the polarity matches the mark on the board. Okay, and finally, you can also get an upgraded antenna. If you do that, you'll have to buy some supporting components like a cable and adapters to get the right connections. So all of this can be had for, I would say, $70 to $100 if you go for the upgraded antenna. Before we get into the assembly of this, which is pretty simple, I want to go over the software configuration, because once this is installed inside our housing, the USB port is not very accessible. So the first thing we're going to want to do is make sure that we have all the right software loaded and configured on our node or a repeater. These ship with Meshtactic already loaded on, but it's probably going to be an older version, and there are some critical bugs that we need to get rid of by updating to the latest software. So let's plug this into the computer, not before attaching the antennas, however, and go through the steps needed to update the firmware and configure it exactly how we need to be a low power repeater. All right, so we've got our device plugged into the computer with a good quality USB cable. I found that's important. And the first thing we're going to do is update the firmware There's a couple ways to do this, and later in the video we are going to be building the firmware from source code locally and flashing through an IDE. But right now we're just going to use the simple online flasher, which you can get to from flasher.meshtactic.org. So these Nordic-based devices are pretty simple to update. We can automatically detect here and select our serial port. Make sure you just have one plugged in and connect to it. It should detect the hardware type automatically, but if it doesn't, you can just do that part in this dropdown. Then we select the latest stable firmware version and follow the instructions. We'll get some notes, and usually you can just continue. So the way these work is they'll enter a mode where they will show up as a USB drive on your computer. You can just verify that here. And then we will download the firmware image and grab it from our file system and just drag it over. Once this is done, it will reboot and have the latest firmware version. Okay, so now that the device has rebooted, we can check the flashing was successful by a few ways again. And the way that we're going to use is the Meshtactic CLI. So I suggest you install this on your computer. Just follow the instructions for your operating system in the Meshtactic documents, and you can check that this is working by typing Meshtactic in your terminal. And to get the information from the node, just type in Meshtactic --info. So now we have all the factory defaults, and we can double check that the firmware version has been upgraded successfully. So there's a couple things that we need to change to make this act as a repeater for us, and I've put these here below, and we'll go through them one by one. Again, there's many ways you can set these settings. Some people may prefer to use the client.meshtactic.org interface, where you can just connect to the device again via serial and set the parameters in this graphical interface. But I found this to be a little unreliable, and you have to kind of keep connecting to the serial port after each setting change. So I'm preferring to use the command line. So the first thing we'll do is set the region to US or wherever you are. Set the appropriate region. It'll write that data to the device, and we do still have to wait for the device to reboot, but that's very quick. The next thing we need to do is set the device role from the default client to router. You can use repeater as well if you'd like. They're effectively the same thing, but router will let the node show up in the nodes list when you query from other clients in your mesh. So router will just do like a priority optimization for the routing algorithm so that your mesh will leverage this node as a point to distribute your messages to all the other nodes. Okay, the next thing we need to do is disable the Bluetooth, and this is just to save power. And I did mention earlier that there were some bugs in Meshtactic that we need to fix, and this was one of them. In the older versions of Meshtactic, if you disabled the Bluetooth on specifically the Nordic-based devices, it would lead to a very unstable system. So they've patched that in, I think, 2.4, and we are good to disable Bluetooth. Similarly, we want to disable the GPS. This kind of only affects startup, which should not be happening very often on a solar-powered repeater, but it'll just let the device bypass the search for a GPS module. It'll make our boot up more efficient. And that's really all you need to upgrade and configure your device to be a low-power repeater. For my purposes, I'm going to do a couple optional steps because I want to decouple my device from like the public mesh, which typically just uses the default long fast modem preset and channel number 0. So I'm going to change the modem preset to long moderate, and I'm going to change the channel number to 2. You really don't have to do this unless you want to kind of have your own private mesh, but this just decreases the likelihood that it's a public mesh. Someone else may be using these settings, and if they're around you, then they'd be participating in your mesh. I found, at least here, that no one really is using these settings, so this will effectively decouple my nodes from everyone else and let me run some very controlled range test experiments. So let's just set these. All right, and now we can go on to assembling the device. So we have our garden light here, which we're going to start taking apart, and our boards, which now have the right software on them. We can go ahead and take off the antennas. And I didn't mention earlier, the Bluetooth antenna goes where it's marked BLE, and the LoRa antenna goes where it's marked LoRa. It may be easy to miss. So these can come off now. We're going to not use any more Bluetooth antennas, and we're going to change the LoRa antenna from this PCB antenna to the SMA connector that's inside the kit. But first, let's go ahead and take apart our solar panel. So here I'm just taking out the screw that holds the panel to the rest of the light. We're not going to need the light part. If you want to, you can keep it on. Okay. And if you do want to keep the light part on, don't follow these steps, but I don't really care about the light part, so I'm going to cut the wires. Okay. And discard the light. Alright, so now I've got my solar panel thing here, and there's just 4 screws that hold it together. All 4 screws out, and this should just come apart. Cool. Just keep the weather stripping on the panel side. And we see we have a lot of space to work with, which is really nice. And the battery actually comes out of this holder, which is really convenient for us. So the first thing that we want to do is drill our hole for our SMA connector. And I am going to do this just right about here. We're going to put the board here, and we're going to solder our battery connector directly to the battery and only use the battery connector on the whiz block. Now, this has a solar charging circuit built in. Maybe you could use the whiz block's solar port and use the charging circuit that's on this board, but I haven't done that. I don't know what would happen. You'd probably get similar results. I just find this to be a lot simpler. So let's go ahead and drill the hole, mount the board here, and solder the wires for the battery connection. But we've got our SMA connector, 7 30-seconds drill bit, and I've turned this battery tab up vertically so I can get some clearance. And I just want to put a hole right about here. Okay, so we've used our 7 30-seconds drill bit, got a hole through the housing, and let's feed our connector through there and glue it down from the inside. So we've got our connector in there. 7 30-seconds is a tight fit, so I used a 9mm wrench to screw it in all the way through, and maybe went a little overkill with the JB Quick epoxy there, but this should be good. Our next step is to solder the battery connector on. And keep in mind from earlier, red is going to go to black and black is going to go to red. I know that's terrible. We can put heat shrink around these to indicate what the colors actually are, but let's go ahead and get this on. And just like that, we didn't even have to use any extra solder. There was enough on the terminals themselves to get this on really nice and tight. Just be mindful that of this antenna pigtail, it's very close to this terminal, so be careful there. All right, now we're ready to mount our board and plug everything in. Let's take our double-sided tape and peel off the tricky part. All right. Okay, and then we'll just put this on the back of the board. And with the USB connector facing the inside, we will just kind of position it like so. Press down. Okay. Next, let's plug in the battery connector. This will only go in one way. Perfect. And then the LoRa antenna. All right. We can gently tuck that like so. Okay. Now we are ready to install our battery. And the board should power on. If the battery is charged. Yeah, there we go. Cool. And that's really all there is to it. I may adjust the double stick tape to actually touch more of these ears, but that's all we have to do. Make sure the LoRa antenna cable is not getting pinched by anything as you close this. We'll screw everything back together. Put the nut on here and attach the antenna. And this is what the final product should look like. And we can probably clean these wires up, but the antenna's on there really solid, everything is sealed, and this should last, like I said, about a week without any solar light. When you get light, it stays above 4 volts, and I'll show you how you can monitor this remotely from another node on your mesh. Okay, so I've got another node set up in a similar way that we set up the router, but now I've configured it to just be a client as default, and of course I've configured it to be on the same channel and using the same long moderate modulation parameters. So to make sure that it is communicating with the solar repeater that we built and put outside, we can just type in Meshtactic nodes, and this should show us our repeater. So we are number 1 and outside is number 2, the rack 4631. So we get some cool information here, but it's not as detailed as if we specifically request telemetry from the device, and that's how I made those voltage plots that I overlaid in the previous part of this video. So to get those, we just type Meshtactic request telemetry, and here we specify the destination as the ID of the node we are interested in. So let's fire this off, and the repeater should get a request for the device telemetry, and it should respond here. And there we go. So we can see that the voltage is at 4.2 volts. And you could like wrap this command in a script and just collect this data over time if you're interested in remotely monitoring your solar nodes. We have some cool information like uptime and so on and so forth. So I just wanted to show you that real quick before we do a deep dive into the built-in range test function of Meshtactic, and also some modifications we need to make the range test work in a really cool way. Let's review the built-in range test module in Meshtactic, explain how it works, and why we want to make some custom changes to the firmware to allow some better results. So in the existing setup, there is a range test module which you can enable and configure one device to be a sender and another device to be a receiver. These are mandatory, and at least in the default setup, the receiver has to be ESP based because we're going to be using the file system to log a file and serve that to the computer via the web client. So yeah, you can use the regular firmware, but just be mindful that there is an automatic timeout so that once you do enable this behavior, it will automatically turn off after 8 hours. And the receiver's role is simply to generate a CSV log file of the special messages that it receives from the sender. So the sender is configured to generate these messages that have a sequence number. They're transmitted over the mesh. And when the receiver receives them, it will log that to a file, including the timestamp, who it came from, and most importantly, the last known position of that device. Now, the sender asynchronously generates position data and transmits that to the mesh. That's what populates the position data in the CSV file. That's how the existing setup works, and you can configure the position data to be updated very frequently, and that'll give you some nice results. However, what I've seen is that the range test messages, along with the position messages, are configured to be what's called, in the Meshtactic world, a polite message, so that if the channel utilization is more than 25%, those messages will simply be not transmitted. And the problem with that is we don't really have any way to know if the receiver maybe just missed a message that was generated or the message was not generated at all. So we don't really have deep insight into our coverage. There's other variables affecting this test, and we do want to eliminate those. So now we're getting into our kind of custom firmware modifications. That's the first one. The second one is that in the existing firmware, the sender does not really log anything. So we don't have anything to compare the receiver's log. We're going to be introducing a new CSV file that's logged on the sender side so that we can do some comparisons. And this will get really interesting when we do a point-to-point test and compare that to a test with a repeater in the middle. And now let's get into the details of the firmware modifications. The changes are pretty simple. There's about 4 or 5 files that we modify. And the first one is in the position module.cpp file. Here we just comment out the code that tells it to skip sending the position if the channel is more than 25% utilized. So we just comment that out and move on to the range test module.cpp file. Here we're going to comment out some more stuff. In a similar manner, we comment out the code that skips the transmission if the channel is more than 25% utilized, and we comment out the code that disables the range test module automatically. Then we add a call to a new function that we're going to write below that saves the sent message to that new CSV file. So this will affect the sender device. The code that we modify can be flashed on both the sender and receiver device just fine. So down below, we basically just copy the function above, which is append file. We copy this whole function and just paste it down below and rename it to append sender file and change a few things inside the function. So we're going to change the CSV file name to range test out instead of range test. And then we also remove a few of the columns that get saved. Okay, and then we have to also declare this in the range test module header file, just one line there. And finally, we make sure that the new file we create also gets cleared on a factory reset. So those are the 4 files that we touch. I'll put a link to the patch if you want to just apply the patch to the firmware directly, or you can just copy what you see here. The last thing I want to mention is that in Meshtactic 2.5, there's a new concept called userprefs.h, and here you can conveniently set a lot of the parameters that we've been manually configuring so that when you flash this to a fresh device or factory reset the device that has this custom firmware on it, these presets will be automatically set. So that's very convenient. You can't set all of the presets, all of the parameters yet, but this is, I think, work in progress and will continue to become better over time. So once we have our sender flashed with the custom firmware and the receiver flashed with either firmware, the custom or the default, we just have to go through a few configuration parameters before we can go outside and start our range testing. So on the sender side, we have to set our position broadcast interval to be 10 seconds, along with our GPS update interval. The GPS update interval tells the device how often to grab a new position from the GPS module, and the position broadcast interval tells the device how often to send that over the mesh. We have to make sure our GPS is working by enabling it and setting the RX and TX pins to the proper pins. This may be different for you, but I'll put up on the screen how I wired my device, and if you want to copy it, you can do the same thing. We turn off smart position and go on to enable the Wi-Fi for both devices, the sender and the receiver. We have to just set the SSID and password and set the enabled flag to true. This will let us grab our CSV files later. Then on the sender, we have to enable the range test and set the sender to 15. This means every 15 seconds, it will send a special message with a sequence number to the receiver to let it know to save that to a file if it's received. Finally, on the sender side, we have to make sure that the position is sent with the most precision. Meshtactic started to obfuscate this for privacy reasons, and if you try and just use the default, I think 13 bits of precision, it's not going to give you very good results. On the receiver side, all we have to do is set the range test to enabled and the save flag to true. We don't have to do this on the sender side because our custom firmware just always saves the data. So this is all you need to go off and do your range testing. Depending on if you set the user prefs or not, you may have to also configure your radio settings. Keep in mind when you do a factory reset, if you don't have those user prefs set, they'll go back to the default state. If you do have them set, they'll go to your state, and our custom firmware will delete both CSV files. We've got our receiver and sender configured, and right now the GPS doesn't have a satellite lock, so it's just sending blank messages, but you can see the sequence number increasing on the receiver. And we're going to go ahead and take these outside, keep this stationary, walk around with this guy, and then collect the data sets that each one is creating and do a comparison before enabling the repeater and doing the same test again. All right, so we've got the receiver in the car, and we're going to go walk around with the transmitter with no repeater this time. Here's our transmitter booting up. We'll get a GPS lock soon and do our initial range test. Okay, we're locked on to the GPS. The receiver's down in the car, and we're going to go for a hike. This will be the baseline test. So the receiver should be getting the GPS location of this transmitter. And keep in mind the transmitter is also logging every point that it is sending, so we can see where we transmitted and didn't pick up the signal. And then we'll repeat this test with a repeater, probably positioned at that weather station down the way. Here's our data exports. I've downloaded the CSV files and used the Python script to plot everything out. And let's just go over what you would see if we hadn't modified any of the Meshtactic firmware. You would see all of the green dots. So the green dots are the receiver's log, and these were just the points that it received throughout the test. Now, what's cool is that we were also logging the blue dots, which were generated on the sender. So you can see that the receiver I've marked was here in the purple marker, and I went for that hike all the way up to the radio tower about here and continued around some water towers here, came back and did a few more trails. I should have kept going because we still got coverage all the way to the end of this trail here, and then went for a drive just around the canyon. So what I didn't expect, and is really cool to see, is that we actually got 2 points received here about almost exactly 1 kilometer away, and that is not line of sight. It's maybe more line of sight than some of these other points that were closer, but that was really unexpected. And then I kind of, like as I expected, as I drove around the canyon, you can see none of these points were picked up. So this is the power of modifying the firmware to get a log of the sender points. And also, I noticed throughout the test that the channel utilization was quite high for some reason. So if we hadn't modified the firmware, a lot of these points wouldn't have even been generated, even though they were at the 15-second interval. So this is a good baseline for our point-to-point test. Point A, again, being this purple marker, and then all the point B's being what you see here. And then the result basically is like, maybe a 300 to 400 radius kind of range, right? With some outliers at 1 kilometer away. So I'm going to go redo this with the repeater positioned at the radio tower here, which has a really good view of all of this surrounding area. And we'll see what the results are for that test next. Okay, so this is just showing the placement of the repeater and the surrounding area. This is of course temporary, as it's not my property. And here are the results. I've modified the script a bit to display a bit more information than we saw in the previous test, but it's basically the same thing. So now we've installed the repeater at the location of this orange marker, and we can see on the visualization a bunch more points. The points in the pentagons are the points that went through the repeater. So we measure this by the hop limit being decremented by 1. Since when the repeater broadcasts messages, it'll decrement the hop limit, and then when the receiver receives that, we can tell it went through the repeater. And when we receive a message directly to the receiver, we have a circle. So that's just indicated by the hop limit still being what it was sent to as the maximum. So all of the points are also color-coded by SNR now. And it's interesting that all of the repeater points, all the points that went through the repeater, even at the furthest distance, still had a very high SNR. So this is 7.25 there and 7.0 there. But you can see the points that went straight to the receiver are quite low at some areas. -2 here, -13 there. And honestly, I think this one here is some kind of bug. I really don't think this reached the receiver directly, and it happens to coincide exactly with the point that went to the repeater. So I'm not sure what happened there, but yeah, as expected, now that we have the repeater, if we compare this to the previous picture, we can see all this extended coverage. Of course, there are areas that we didn't get coverage, and this is due to terrain. So I want to compare this to an RF simulation, which I'll show next. But yeah, overall, really happy with these results, and I hope you found this methodology interesting, and maybe it's something you can use yourself as well. This is an RF simulation of the transmitter, and we can see the green areas are where the signal is strongest, and then due to the terrain, the signals are a bit weaker in the blue and dark blue areas. Now, this isn't perfectly accurate, and it is interesting to see that we actually did pick up points in some of the darkest blue regions in the left side of this image, and then didn't pick up those points in the beginning of the canyon drive where it is a bit lighter and closer to green. So this isn't perfect, but interesting to see nonetheless. Also, here's a simulation of the first test, and now you can see why I think that point on the far right was an anomalous data point. There's basically no coverage there, and everything else does seem to coincide with this simulation. Cool, so just to recap, on the left side we have our point-to-point test, and on the right side we have our test with the repeater in the middle. So we went from about a 300 to 400 meter reliable radius to, I think, well over a kilometer. If I kept driving and extending this test out in all directions, we would have seen the SNR from the transmitter to the repeater drop quite a bit, and we didn't yet. So maybe even multiple kilometers, and I'm thinking for a future test it would be really cool to put the transmitter on a drone and just send it out to see how far the system can go. But in any case, I hope you found this video interesting, informative, and useful. It was a lot longer than I anticipated, but it was a lot of fun and a lot of work to make. So hope you found it valuable. If you made it this far, let me know what you'd like to see for future videos. I think I'm going to be branching out a bit from just strictly radio electronics. We started with SDR videos, now some Meshtactic videos, to more general purpose and maybe beginner-friendly educational videos.